Okay guys, time to do some math.
Alright, in this video I'm going to teach you a technique called U substitution, which is a device used to undo the chain rule. So it is an integration technique that allows us to anti-differentiate a chain rule scenario. So it's used whenever we have a compound function or a function inside of another function, like this. So for example, if you look at this integral, because I have a function inside of a function and some other stuff going on, in this case, I am going to use U substitution. So anytime that I see a function inside of another function, I'm going to attempt this process that I'm about to teach you called U substitution. And the whole premise of U substitution is that we are going to replace some portion of the function with an easier function to deal with. And we're going to call that function U. So I'm going to kind of code switch here. I'm going to change languages. Instead of being in X and anti-differentiating with respect to X, I'm going to write a new integral that is speaking the language of U and anti-differentiate with respect to U. So here's tip number one. Tip number one is to let U be the innermost function. So I'm going to look at this function and I'm going to say, what is the function that is at the inside of some other function? And the answer is sine of x. This is inside the x squared function. So I'm going to come over here and just say that U is going to be sine of x. And again, what I'm trying to do is swap out something that is slightly complex for something that is simpler. So tip number two, this is kind of the tricky bit. We're going to evaluate du, because as you know, when I integrate something with respect to x, if I'm speaking the language of x, this dx indicates to me that I need to anti-differentiate with respect to x. So if now I'm switching my integral to speak the language of u, I need to anti-differentiate with respect to u. So I need to find du. So let me just pull this over here and see if I can explain this way. If I look at this new equation that I've established where I'm letting u equal the sine of x, and if I attempt to use this notation that we learned back when we looked at implicit differentiation, this means take the derivative with respect to x. And if I were to go through and do that for this equation, I would end up with the derivative of u with respect to x, which is du over dx, and then that would equal the derivative of sine of x, which is cosine of x. And then remember that technically what we're doing here is we are doing the chain rule. So I'm taking the derivative of the outside, evaluated at the inside, times the derivative of what's inside. And the derivative of what's inside in this case is dx over dx. So this next step is where we're going to have a slight deviation perhaps from what we've thought before, and that is that I'm trying to isolate du. I want to get du all by itself so that I can integrate with respect to u. I'm trying to generate for myself a du term. So I'm going to try to get rid of this dx term by multiplying both sides by dx over 1. And I'm treating these just like variables now, so these guys cancel each other out. And then if I come over here and I multiply all this by dx as well, those guys cancel each other out, and I'm left with du is equal to the cosine of x dx. So I have my new set that I'm going to use to establish a much simpler integration problem. And let me just say this, the description that I walked you through just a second ago over here is kind of a formal argument for how to create du, but it's just as effective to sort of think about the shortcut of this you can sort of think of it this way. If you've got u, you can differentiate u, which creates du, and if you differentiate the right-hand side, you get the cosine of x. And if we, again, just play with our chain rule and multiply all this by the derivative of what's inside, you can argue that the derivative of x we can call dx. So this is sort of the shortcut version. We'll look at a bunch of examples to make this a little bit more clear, but if you're ever confused on why is there a dx term in here, the best argument is found right here. So run yourself through that again, if need be. But anyway, let's try to continue with this u substitution structure. Tip number 3. We're going to create a new integral with u and du. So let's try it. What I'm trying to do is create this exact same statement by using u and du. So let's see what we got. Sine of x to the power of 2. I'm letting u equal sine of x, so I'm going to write this as u to the power of 2. Instead of sine of x to the power of 2, it's just u to the power of 2 because u is the same as sine of x. And then, notice what happens here. I've got all this extra garbage, right? I've got this cosine of x times dx. But what's super cool about this is that when I write du is equal to the cosine of x times dx. So by simply writing u to the power of 2 times du, I am incorporating all of this garbage that was my original antiderivative. And this is great news because even though when I looked at this, I didn't know how to antidifferentiate this, I do know how to antidifferentiate this. So let's try that. Bam! Easy. 1/3 times u to the power of 3 plus c. I'm remembering the plus c because I have an indefinite integral. And now, of course, I'm not done because this is I've got to translate this back, right? The answer to this antiderivative is not 1/3 u to the power of 3 plus c because it's like, what even is u? So what we need to do is translate this back into the language that we originally were speaking, which is the language of x. So if this is my final answer, and if I know what u is, because remember that we let u equal the sine of x, I can do one final substitution where I let u equal sine of x, and I can rewrite my final answer as 1/3 multiplied by the sine of x to the power of 3 plus c. And there we go. We are done. And if we want to prove to ourselves that we are correct, we can take the derivative of 1/3 sine of x to the power of 3 plus c, and I promise you that we will get this original function that we started with. Okay, let's just prove that to ourselves real fast. Take 3 times 1/3 and you get 1, and then you're going to have sine of x. If you lower your exponent by 1, you'll have 2, and we need to make sure that we do the chain rule. I've taken the derivative of the outside, evaluated at the inside, times the derivative of what's inside, which would be the cosine of x. And voila, we've got that, which was what we started with. Let's look at one more example and just run through this all in one swoop and see if this begins to click into place a little bit for us. So I've got this big gross antiderivative, 3x squared times sine of x cubed. And we're going to begin by letting u equal the innermost function. So what I'm doing is I'm looking for parentheses, and I'm trying to find what is the function that is at the heart of all of this stuff. And this x cubed term is inside of the sine function, so that gets the vote for the innermost function. So u is equal to x cubed, and then du is going to be the derivative of u, which is going to be 3x squared dx. I'm doing my chain rule, the derivative of the outside, evaluated at the inside, times the derivative of what's inside. So using u and du, I'm going to try to rewrite this antiderivative, or this integral. So here we go. this says the sine of x cubed, and I know that x cubed is u, so I'm going to write the sine of u. And think of it this way. Now we have dealt with all of that. And the leftover bits are 3x squared and dx. And what's awesome is that when I look at this, those are the pieces that I see. So by writing du, I am incorporating 3x squared and dx already. And this is great because I do, in fact, know how to anti-differentiate the sine of u. That would give me negative cosine of u plus c. And to wrap this up, again, this clearly isn't the answer because I didn't start with u's, I started with x's, so we need to convert this back into the language of x by substituting in our value of u, which we let be, x to the power of 3. So final answer is negative cosine of x to the power of 3 plus c. And just for good measure, let's take the derivative of this and make sure that we get 3x squared times sine of x cubed. And we do, because the derivative of the negative cosine of x is going to be positive sine of x cubed. This is the derivative of the outside, evaluated at the inside, times the derivative of what's inside, which is the function that we began with. So if you're feeling like these examples are kind of canned because they worked out so nicely, you are absolutely correct. I showed you these two examples first because everything just worked out super, super nicely and easily, and our du term ended up being all the other extra stuff. And the question is, does that always happen? And obviously the answer is no, that does not always happen. So in the next video we're going to look at some more complicated u substitution problems in which all the extra garbage might not equal our leftovers.